Hi, Damien. We'll get started here in just a few. Thanks for your patience. All right, let me go ahead and share my screen. So can you see the screen on the homepage? Okay.
Yes.
Okay. All right. So here we are this week. This week's material, we're going to be dealing with waves. This is a fairly short lesson to cover because there aren't many things that we'll be calculating for waves. So you can see from the objectives, we're going to look at something called the universal wave equation. We'll look at the different types of waves. We'll look at the parts of a wave. We'll look at properties that we measure for waves to help us analyze and describe wave motion, wavelength, frequency, and velocity. We'll talk about the interaction of waves and matter when we get into sound waves, and we'll look at problems that deal with the relationship between the speed of sound and temperature. Okay. So as a reminder of the activities that you need to get done this week, there's a discussion dealing with waves that you need to complete. And problem set number 11, which actually deals with last week's material on thermodynamics. I know that there was some type of mix-up. I'm almost sure of it last week, but if you need a video on thermodynamics, there is a video in the extra note, in the extra video. There's one for actually for thermodynamics. So if you click the link in the announcements, you see there's a video. I believe the momentum videos has a portion that deals with thermodynamics. Momentum, work, energy, and thermodynamics are all grouped together under this one video. Okay, so that can be of some help to you to complete problem set number 11. Okay, and then of course you have, oh, sorry, wrong one. You have a group of resources that deal with waves. and that's under required readings viewings. That's chapter 11 in the textbook. And then there are some videos dealing with waves. And then here are the notes that I'm going to cover for you dealing with waves. Okay, so we can jump right into the notes. Bear with me for a second. Hey, I'm in class.
Quick question. Where we vote at the courthouse?
Yeah.
Okay.
Sorry about that. That was my spouse calling to ask where we vote. All right. So in this particular material, we're going to be looking at a specific type of motion, oscillatory motion and wave motion. And you'll see that they kind of go hand in hand with each other. So what is an oscillation? So this type of back and forth motion, okay, that's constrained between 2 points. We've dealt with a lot of different types of motion so far: horizontal motion, vertical motion, projectile motion, circular motion. We've dealt with force and momentum. We've dealt with collision type motion. So now what we want to do is have a way of describing motion that's back and forth, okay? Like a swing as it oscillates back and forth, or a pendulum, okay? Atoms and molecules also oscillate, but we won't get into that type of motion. That's, much more complicated than what we want to analyze. We want to look at simple things like a pendulum or an object on a spring that's bouncing back and forth. So the reason we are interested in that type of motion is because when something oscillates, it can create a wave. And a wave is nothing more than a disturbance that moves from whatever it was created, wherever it was created or whatever was disturbed. Okay. I like to say that a wave is organized energy moving through some type of medium. And in many instances, the medium is water or air, or in this case, they give here an example of a guitar string. When you pluck it, it's oscillating back and forth, and it creates a sound wave in the air. Okay. Another example is an earthquake. And in that particular case, you have organized energy traveling through the ground, where the ground is the medium, and the wave is this organized disturbance of energy. Okay. And so it also indicates here that things without mass can oscillate. A guitar string, air, and the ground, water, they all have mass. But things without mass can also oscillate, like light. And light does not only mean visible light, it can mean any form of electromagnetic energy. Things like radio waves, microwaves, gamma rays, X-rays, all of those things are examples of light or electromagnetic energy. Visible light is only a small part of the electromagnetic energy spectrum. And those types of, that type of organized energy can travel in empty space, or vacuum as we call it. So those types of oscillatory motions that I just discussed obey Hooke's law. Okay, and you notice it says here the simplest type of oscillations. And of course, at this level of a course, that's what we want to focus on. The simplest types of back and forth motion, the simplest types of waves obey Hooke's law. And in the box, you see Hooke's law stated as F equals minus Kx. Okay, so F is force. And what's important about that type of force is that it's a restoring force, meaning that type of force always wants to bring the oscillator back to its equilibrium position. Okay, in this formula, X is the displacement, meaning how far is the object being moved from its equilibrium position. The displacement from equilibrium. We know that word equilibrium means balance point, right? Equilibrium in this case means the position of stability. Okay, and so that's why we call it the equilibrium position or the stable position. All right, and in this equation, K is called a force constant, and the units for the force constant go right along with force per unit displacement or newtons per meter. Okay, and it tells you how rigid or stiff your oscillator is. A larger force constant, big values of K mean that the system is stiffer and therefore going to need or create a larger restoring force. Now, you might notice also in this formula, there's a minus sign. That minus sign is because it's a restoring force. So whichever direction you stretch it or disturb it from equilibrium, a restoring force brings it back in the opposite direction. Period and frequency. Well, we've seen this type of symbol before, period, T, when we talked about circular motion. And that is because circular motion is periodic. Okay, oscillatory motion is periodic. Wave motion is periodic. So why? Because circular motion, oscillatory motion, wave motion repeats itself at regular intervals. Okay, so it's repetitious. Okay, and the time for one oscillation is the period. When we talked about circular motion, the period was the time to make one trip around the circle. Here is the time for one complete oscillation. Oscillation means that the object has a starting point, it moves from that starting point, and when it comes back to that starting point, that's one complete oscillation. Okay. The frequency, that's another property that we measure for our oscillatory motion. Okay, and that's the number of cycles per unit time. So period is the time for one cycle. The frequency is the number of cycles per unit time. Okay, and the unit in the metric system, the SI system, for frequency is the hertz. We already know the time, the unit for a period, because that's time, that's in seconds. But we have a new property called frequency. So its unit that we have not dealt with is hertz. And you can express hertz as, use hertz to express cycles per second. Okay. And you can see in the box that there is a relationship between period and frequency, and that is the frequency equals 1 over the period. They are inverse. So frequency equals 1 over period, period equals 1 over frequency. Okay. So if we're dealing with a simple harmonic oscillator that obeys Hooke's law, the motion, the oscillatory motion that it will exhibit is called simple harmonic motion. So simple harmonic motion can be described by Hooke's law, and a system that exhibits simple harmonic motion is called a simple harmonic oscillator. Okay, if our motion is simple harmonic motion, then it obeys Hooke's law, and the maximum displacement, the maximum that we stretch it or move it from the equilibrium is called the amplitude. Okay, so they give an example. If we have a spring and we attach an object to a spring and we connect the spring on one side, we support it, attach it to the wall, for example, and we pull that spring out and let it oscillate That's an example of a simple harmonic oscillator. And for our simple harmonic oscillator, a spring in this case, we can find the period, the time for one complete cycle by taking 2 times pi times the square root of m over k, where m is the mass, and remember k is the spring constant. So here's a visual of a simple harmonic oscillator or simple harmonic motion. That's our mass on a spring. So you can see in the far left, it's not being stretched at all. Once you let it go, it will stretch and establish an equilibrium position. That equilibrium position means you can think of it where it's like at a position where before it starts to oscillate, it's stationary. If you slightly disturb it from that equilibrium position by stretching it a distance x, the amplitude in this case, it will oscillate between minus x and plus x. Notice the x equals 0 is the equilibrium position. So the stretched position before it oscillates is called the equilibrium position. Once you disturb it, it will oscillate back and forth between plus x and minus x. The maximum stretch is called the amplitude here, okay? Another example of a simple harmonic oscillator is a simple pendulum. Now, we don't have to get too deep into knowing what a pendulum is. If you've ever looked at a grandfather clock and you've seen the pendulum bob swinging back and forth, that's what we're talking about, a simple pendulum. Or imagine a swing, for example. So a child on a swing, and you pull the swing out, and then you let it go, and it will move back and forth in a pendulum type motion, okay? So if we're dealing with a simple pendulum, which is another simple harmonic oscillator that exhibits simple harmonic motion that is controlled or explained by Hooke's law, the way we find its period is to take 2 pi times the square root L over G. So you can see for a pendulum and for an object that a mass on a spring, the formula for the period looks very similar. It looks very similar, okay? So we can see, let me minimize this. I'm gonna open up a whiteboard, okay? And let me stop share, and I'm gonna share again. I'm gonna share the whiteboard. Okay, so we can see we have 2 formulas here. T equals 2 pi square root M over K. That's for our spring system. Okay, and we pick another color here, black here, we'll use that. And then T equals 2 pi square root L over G. And this is for our pendulum. And you can see, just by looking at that, they look very similar. In fact, if we set them equal, 2 pi square root L over G equal to 2 pi square root M over K. Just want to make sure. Right. Then we can see that our 2 pi's cancel out, and we're left with, if we square both sides, we get L over G equals M over K. Okay. And let's say, for example, we wanted to know the value of our spring constant, okay, or K in this instance. All right. So K is equal to M times G over L. So there's a direct connection or a direct similarity between oscillatory motion for a spring and oscillatory motion for a pendulum. Okay, so let me go back and share. Oh, let me stop here. Let me go back and share that. Oh, there we go. So I also mentioned to you that there is a connection between circular motion and simple harmonic motion. Circular motion is periodic. Simple harmonic motion is periodic. They both have a period, right? So what's the connection? If we take our circular motion and trace out a point along a sheet of paper as it oscillates, it will create, you would learn if you in a trig class, something called a sine function, a sine wave or a cosine wave, right? Meaning it's repetitious or periodic. Okay. We don't get too deep into damped harmonic motion. What you need to understand about this is that it is no longer simple harmonic motion, because if we introduce friction, anytime we introduce friction or allow friction to interact with our harmonic oscillator, then it will undergo what's called damping. And that's about all we need to understand for that. Okay. Resonance. So resonance means that you have one thing vibrating, and it forces another system to oscillate at the same frequency. Okay, it will force another object to vibrate at its natural frequency. Okay, resonance, at one object forcing another object to vibrate at the same frequency, or to oscillate at the same frequency. Okay. So now we get to what's called the universal wave equation, which relates wave speed, how fast our wave is moving to that wave's frequency and wavelength. Okay. So we call the wave speed V with the subscript W for wave speed. That funny upside down looking Y is called lambda, and it is for wave length, the length of our wave. And then amplitude, which is the height of our wave. So notice what we're doing to determine the speed of our wave is multiplying the frequency, which is the number of times the wave repeats itself per second, number of cycles per second, times the wavelength, which is the distance from one peak of our wave to the next subsequent peak. The distance from peak to peak on our wave is called the wavelength. Notice that the wavelength has nothing to do with the amplitude. I'm sorry, the wave speed has nothing to do with the amplitude in our universal wave equation. Okay. What types of waves are there? There are two types of waves. One is called a transverse wave, and the other is called a longitudinal wave. So bear with me just for a second, please. Sorry about that. It's my daughter calling me, asking me about voting. All right. Well, at least, folks are trying to vote. So, all right. So, two types of waves, a transverse wave and a longitudinal wave. And you can see in the picture, they're very different. A transverse wave creates a disturbance perpendicular to the motion of the medium. In the picture, the medium is the slinky, and the slinky is moving up and down, but the wave or the disturbance is moving to the right or forward, okay? A longitudinal wave, on the other hand, notice in this particular case that the slinky is moving, it's actually vibrating left and right. And you can see in this case, the disturbance or the wave moves parallel to the disturbance. To the motion, okay? So for longitudinal wave, the medium is vibrated back and forth, left and right, if you want to look at it that way in the picture. But the energy or the disturbance actually moves to the right. Okay. So now, why is it important to know about those two different types of waves? Well, number one, transverse waves are all light waves, whether it's visible light, X-rays, gamma rays, microwaves, radio waves, any kind of electromagnetic disturbance is a transverse wave. Longitudinal waves, on the other hand, are sound waves. Okay, remember, light waves don't have to have a medium, but sound waves or longitudinal waves do. We won't get too deep into superposition and interference. Both of those terms, superposition and interference, means we're adding or combining waves. Okay, and we can add or combine waves so that we get a larger wave, which is called constructive interference, or we can combine waves so that we get a smaller wave or cancel out a wave completely, and that's called destructive interference. Okay. Intensity. So as I said to you, a wave is organized energy. It is the energy that's moving. Okay. It's the energy that's propagating. And that energy, that wave, has an amplitude, and the amount of energy is related to the amplitude. More amplitude, more energy. It's like comparing a small water wave to a tsunami wave. Which one's gonna have the most energy? Which one can do the most damage, right? Okay. And so to find and the intensity, we relate that to the amplitude, and the way we measure that is with decibels. Okay, watts per meter squared, decibels. That relates to the amount of intensity. Okay, and so power per unit area. is how we measure intensity. We don't use decibels because that's like, English or imperial units. In the metric system, we would have watts per meter squared as a measure of intensity. Watts for power, meter squared for area. Okay, intensity. All right. So that's the basics of wave motion and simple harmonic motion. But there is something else that I want to cover with you, and that deals with the speed of sound. Okay. So let me go into our extra resources. Right under the announcements are our extra resources. And we click on that link. Remember, there's a folder for every topic. And here's a folder on waves. Okay. Now I'm going to go into this folder, but I'm not going to go into every one of these sets of slides. I'll just cover a few of them that can be of use to you, and you can use the remainder of them as you choose to, as reference or research or resource material. Okay. The first slide item I want to bring up deals with the relationship between the speed, the wavelength, the frequency, and the period. Okay. So this formula that you see here deals with the speed of a wave. This V represents the speed of our wave. Our wavelength lambda, remember that upside down funny looking Y is lambda, that's a Greek letter. That stands for wavelength in meters. And then we have our frequency in hertz, or since frequency and period are reciprocal or inverse of one another, we can replace the frequency with 1 over the period. And either of these formulas, wavelength times frequency or wavelength times 1 over the period, will give us our wave speed. That's the universal wave equation. And recall the relationship between period and frequency. Frequency is period, is the time it takes to go from one peak to the next in our wave. And the unit is seconds. And the relationship between period and frequency is period equals 1 over frequency. Seconds equals 1 over hertz. Seconds for period, 1 over hertz for our frequency. Or we can say frequency equals 1 over the period. Hertz for frequency, 1 over seconds for period. The definition for frequency, recall, is the number of peaks per second, and it's measured in hertz. Okay, so this is kind of like a summary screen of the various properties that we can measure when we're analyzing wave motion. Okay, and then here is an example of that formula being used. Okay, it says an earthquake produces a wave that has a wavelength of 417 meters and travels at a speed of 5,000 meters per second. And they want to know what's the frequency. So here we have our pyramid that deals with the relationship between speed, wavelength, and frequency. Well, we want to find the frequency, so we cover it up, and it tells us that we have to take our speed and divide by the wavelength. So that becomes 5,000 meters per second divided by 417 meters. That gives us 12 hertz. So be careful to deal with the units correctly, because if you tell me that the unit is 1 over seconds, if you tell me 12, 1 over seconds, I'm going to mark it wrong or take points, because you have to properly resolve 1 over seconds as hertz. That's how the units work out here. Meters per second divided by meters gives us our 1/seconds, which is equivalent to hertz. Okay, so that's how the units work in this particular case when we're dealing with, the relationship between the various properties that we measure for our wave. Okay, all right. I took that equation and I showed you both versions. If you want to find speed by doing wavelength times 1/period, that's meters times 1/second. That gives you meters per second. Or you could do speed equals wavelength times frequency, and that gives you meters times hertz, meters per wavelength, hertz per frequency, which is equivalent to meters times 1/second, which again gives you meters per second. Okay, so that's how you properly resolve the units, no matter what form of the universal wave equation you want to use. Okay, the other thing that's really important for us to understand is how to determine the speed of sound, because sound is an example of a wave. Sound is a longitudinal wave. Okay, and for any sound wave, it will travel 344 meters per second in air that's at 20 degrees Celsius. So if you go outside and it's 20 degrees Celsius, that's how fast sound is going to travel. Sound has to have a medium. Okay, and how fast it moves will depend on what type of medium. Sound travels better, solids, liquids, and solids. Okay, actually it's solids, then liquids, then gas. Okay, and sound has to have a medium. It cannot travel in a vacuum. Remember, light can travel in a vacuum, but sound must have a medium. Okay, how fast the sound will travel also depends on the temperature of the medium. Okay, it also depends on the temperature of the medium. Okay, so you can see here, if from this formula we can determine how fast our sound wave is going to travel. Okay, how fast our sound wave is going to travel. So we start with a baseline of 331 meters per second. And for every degree Celsius, we add 0.6. So if we take our temperature, please do not mistake this T in this formula for period. This T in this formula is for temperature. If we take our temperature in Celsius and multiply it times 0.6, we then have to add that to 331 to figure out how fast our sound will travel. So for example, I'll work an example for you here. If the temperature is 45 degrees Celsius, we take 45 degrees Celsius, we multiply it times 0.6, that gives us 27. Our Celsius cancels out, and that's 27 meters per second. We add that to 331 meters per second, we get 358 meters per second. So if the temperature outside is 45 degrees Celsius, sound is going to travel at 358 meters per second. Okay, so that's how you find the speed of sound, right? Depending on the type of medium and the temperature of the medium. Okay, I have some other notes in this packet that are good if you want to just learn more about things like music, noise, resonance, harmonics, interference, and acoustics. We don't really dive deep into that too much. Resonance is one of those things that we do focus on. I covered it a little bit in the previous packet. So resonance is forced vibration. So as I said before, you have one object vibrating that forces another object to vibrate at the same frequency. And that makes the sound seem louder because you have more things vibrating. Okay. And it's useful when we want to tune instruments like guitars, pianos, and so on and so forth. Resonance is helpful in that respect. But resonance also has a destructive side. So when you force an object to vibrate at its natural frequency, you can actually damage it. For example, if the opera singer sings the right note and causes the glass molecules to vibrate at their natural frequency, the glass will actually shatter. So that's an example of resonance. We also see resonance at play during an earthquake, for example. If you see like a bridge vibrating, that's because an earthquake is a seismic wave. That wave has a frequency. That frequency, if you recall, is associated with energy. That wave carries a certain amount of energy depending on its amplitude. Okay. And so as the energy from that seismic wave or earthquake wave is shared, as that energy gets transferred to the molecules in the bridge, they will begin to vibrate or oscillate at their natural frequency, which is not what solids are meant to do. And so that will cause damage to the bridge. Okay. Now, what you see in the picture here is a bridge vibrating because of a wind tunnel kind of effect. Okay. So the wind actually caused the bridge to start to vibrate at its natural frequency. Okay. All right. So as I said, that this was going to be a fairly straightforward and short block of instruction. I can share this whiteboard when I post the recording. Do you have any questions for me, Daniel?
No, ma'am. I'm just gonna keep looking at the recording to figure it out. Hello?